Hello and welcome back to Calculus 3, section 11.8, arc length. So, want to know the length of the curve in space. And we have, let's find some kind of, there we go, curve. So we have this particular curve. And in some cases, it's easy to stretch the curve and measure, but in some cases, like a road that winds around the mountain or something, you can't really stretch it and measure it. Yeah, you can drive on it and measure it, but why simple if you can complicate things? So we can find the length of the curve using calculus and our vectors. Now, first, we are going to review real quick from Calculus 2. So, Calc 2, we had the arc length where we said that you take a look at any curve, you take 2 points, and you look at the length, which is a straight line. So, if we are to draw this thing larger, it would be something like this, and the real curve would not be the one that we compute. So if this is delta x and this is delta y and this is some, let's say, lowercase l, we can write Pythagorean theorem where L squared is equal to, well, L is equal to square root of delta x squared plus delta y squared. And then we do a little manipulation where we pull out delta x. Oops, I put L in. L is equal to delta x as we factor out delta x squared. So we get delta y over delta x squared. So we know that that in the limit becomes the derivative. So we are able to obtain the formula in Calculus 2, which says that the length of the curve is the integral a to b square root of 1 plus dy dx squared dx. So this was the formula. We still need this. We still need this formula, and we're going to come up with two new formulas. So in this case, let me just check the stream. Stream is live and working. So when we are looking at this formula, we should check whether this is one-dimensional, because we know length, it's one-dimensional. And, roughly speaking, just the orders of magnitude, the square root will cancel the square, leaving the derivative, and then derivative and integral cancel down to a function. Therefore, it is one-dimensional because you only have just function floating around. That's 1D. All right, so dimension-wise, it's okay. It is length. And what we are interested in Calc 3 here are the other forms of this equation. And mainly that would be, let's say, first, parametric, right? We want to see the parametric form. So for parametric form, we can, so let me actually get a title. Now this derivation would be important for our honors option students to know, because this could be an exam question. So what is the parametric form? Parametric form would be when we take L, which is a to b square root of 1 plus dy over dx squared dx, and we multiply this one with dt over dt. So what I'm going to do is I'm going to now combine, put these two guys in this peanut, so dx over dt, and I'm going to shift that under the square root. So what I get is that L is equal to integral. Now I'm going to change a and b into alpha and beta, because there's not the same a and b. Remember, we are changing now the variable for the problem. We are going from x being the independent variable to t, which becomes the parameter independent variable. So I'm just going to change a and b into alpha and beta. And I'm going to have under the square root dx dt squared times 1 plus dy dx squared. And then we have dt on the outside. Now, there I say clearly, the dx over dt squared times 1 is going to be dx over dt squared plus, and now dx squared and dx squared cancel, and you are left with dy dt squared, everything dt. Now, those of you who studied so far, you guys are recognizing here the f prime squared plus g prime squared. I'm just going to put like this: f comma g are components of good old vector r of t. So now, if you are given r of t, which describes that curve in the space, you pick its f and you pick its g, take derivatives with respect to t, and plug them in to get the arc length. So what we are going to now box is a 2D version and a 3D version of the parametric form for arc length, which is alpha, beta, or a to b, doesn't matter, square root of dx dt. Well, actually, let's just call it f prime of t squared plus g prime of t squared dt. And the 3D version will just have another function underneath. So f prime of t squared plus g prime of t squared plus h prime of t squared dt. So that will be parametric approach. And I'm just going to make a note here in blue. This is the notation for the 2D r squared output. Note that for r squared we have r of t equal fg, and for r3 fgh. Happy? Almost. Awesome. So now let's take a look immediately at an example of this. You have the ones that are given in a textbook. That's the ones, you know how to read these. All right, so here's the problem 16. it says r of t is given as 4 cosine t, 4 sine t, 3t. What is this? Did anyone study? Helix. So 0 less than t less than pi. Find arc length. Find the length. Right, have fun. No pressure, 18 seconds. No problem. Are you guys get 7?
Yep.
No, good, because that will be wrong. Let's see what the answer actually is. 5? All right.
The answer is the integral of the square root of the sum, the derivative squared.
So length would be integral 0 to 6 pi, integral of square root of, and now each one of these derivative and then squared. So it's going to be 16 sine squared t plus 16 cosine squared t plus 9 from dt, right? So that's 25, which is 5. So the whole thing is integral of dt, 0 to 6 pi, so 30 pi. $18, I told you. So what happened here? You factor out 16, you have sine squared plus cosine squared, which is 1. So you're left with 16. 16 plus 9 is 25. Square root of 25 is 5, which I kick in front. Integral of 5 is just 5t. So 5 times 6 pi is 30 pi minus 0, right? So 30 pi. Done. You want another one? Of course you want another one. Exactly. We want a 2D or a 3D? What's better? 3D is better? Okay. Number 19. So R is given as e to the 2t, comma, e to the 2t plus 5, comma, e 2e to the, oh no, this is 2. 2. Okay, 2 e to the 2t minus 20. I just fix it. 0 less equal than t less equal than ln 2. So it's e to the 2t, 2e to the 2t plus 5, 2e to the 2t minus 20, and then 0 to ln 2. "23 seconds, no pressure." If anyone else has the answer 6? Just crickets.
not one.
One, two, three components, so it's a 3D vector. Derivative of this will drop 2 down. When you square that, you get 4e 4t. Derivative will drop 2 and 2 is 4 squared is 16, e to the 4t again. Derivative of plus 5 is 0, so that's gone. Same thing happens with the minus 20. 16 plus 16 plus 4 is 36, whose square root is 6. And you factor out e to the 4t, which becomes e to the 2t. When you integrate e to the 2t, you get e to the 2t over 2. 2 kills 6, you get 3. You plug in upper limit ln 2. 2 goes inside of ln, 2 squared becomes 4. E and ln cancel, you get the 4 there. E to the 0 is 1. 4 minus 1 is 3 times 3 times. Alright? Questions, concerns, just questions. Right. See? Not a problem. Go home, do another 10 of these, you'll be golden. Right, Mark? The parameter thing, yes. All right, so now we talked about the parameter being the time, but we can also use theta or angles to be the input in terms of the parameter. So now we have to do even crazier algebra to do this formula because we want to change the parametric form into a polar form. Remember, in the polar form, it was r comma theta as inputs, and then r is equal to f of theta. So for the polar form, we can use the substitution because it's a product rule, right? Between it's x equals r cosine theta, so that's a product rule. I can work it out. Actually, maybe we should review just a tag, so there are no issues. Well, there will be issues, but let's try to minimize issues. So for polar, we start at the point, which was r theta. Then we have the function, which was r equals f of theta. And then we had the conversion, where x was equal to r cosine theta and y equals r sine theta. But for this pair, you see this r is a function. Of t. So r is a function of t, which means that every time when you have to take a derivative of this, you have to use the product rule because you have r, which is a function of t, times cosine theta, which is also a function. I mean, function of theta, not of t. Function of theta. So everything is over here as a function of theta. So now, if I want to find dx d theta, I will have to work out the product rule. So that will be we can call this f, right? So f times the derivative of the second, which is negative sine theta, plus f prime times cosine theta. So this is all theta, these f's. So we have that the dx d theta is f prime of theta cosine theta minus f of theta sine theta. So we are able to develop the first formula for dx's. Now dy d theta is going to be, again, you're differentiating the relationship between y, r, and theta. So once we differentiate that, again, copy the first one, which is f times the derivative of the second, which is cosine theta, plus derivative, so derivative of r, so it's f prime of theta times sine theta. And now we have these two. If I am to take the good old arc length from alpha to beta, the square root of dy dx squared plus, dx dt, dy dt, dt, and we are simply to interchange variables where t is theta. The arc length becomes dx d theta plus dy d theta and erase dt. D theta, that's what I said, please pay attention. Look. Oh, that's not the end. Oops. Plug in this, and when you clear out algebra, you get the one that we actually want. And that's the one we want. All right. Example time. So problem, I don't know, whatever. Problem 36. Find the length of the spiral. Nah, they're parametrization, just a different form. So find, okay, of the spiral, and now we write the spiral. Spiral is r equals 4 theta squared. From 0 to 6. So we know that this f is r, right? So we have r, well, no, f. F is 4 theta squared. And what's f prime? 8 theta. So all we need to do is to plug in. Function squared plus derivative squared. That's what I said. I was just testing it to see who's awake. Now what? Factor out 16 goes out, and factor out theta squared goes out. So when we factor out 16, jumps out, it's going to be 4. And then single theta here. We factor out everything from the first one. Plus, and what's left in the second one?
Yeah, it should be theta squared plus 4, right?
Yeah, that's what I have. D theta. course, cool, man. How do we integrate this? Good thing we don't have a shed, yeah. Just use sub, right? Have a square over there. Can you do trig substitution? Yes, by all means, please.
Why would you?
Well, some people like pain, you know. So yes, the U sub is the way to do this. I'm gonna do trig sub just because I can. So you have to look at it. No, actually I won't. I'm lazy. U equals theta squared plus 4 du equals to 2 theta d theta. So we need to steal 2 from 4. Awesome. We have 2 integral from 4 to 40. New limits, right? Because we are changing into U domain, so plug in 0 in the U substitution and then plug in 6 one at a time. We have U to 1/2 du, which is 2 times U to 3/2 over 3/2 from 4 to 40, which is further 4/3 U to 3/2 from 4 to 40. That would be 4/3, open parenthesis, 40 to 3/2 minus 4 to 3/2. Now the second one is clearly 8. The first one is a somewhat issue. So 4/3, and I know I can take the square root of 4. That would be 2, but then it stays 10. 10 can be worked out. So it's 2 root 10, and I need to cube that, so 80 root 10 minus 8. Right, the 40 you can write 4 times 10. Square root of 4 is 2, square root of 10 is square root of 10. Cube the 2, you get 8. Cube the root 10. Yep, 2 go out, make a 10. Okay, good. So technically, that's it. Now we can pull out 8 if you are really interested. Right, you can pull out 8. So 32/2, 10 root 10 minus 1. You pull out 8. 8 times 4. I can. What happened? Details over 3.
That's an important detail.
Yeah. So square root of 40, that's 4 times 10, square root of 4 is 2, square root of 10 is 10, square root of 10. And then when you exponentiate, that 2 in front of 2 to the 3 is 8. And then you have root 10, root 10, root 10. 2 root 10s make a 10, so 80. And then root 10. Minus square root of 4 is 2, cube is 8. So you get that expression, factor out 8. 8 times 4, 32 is done. Awesome. Another example? That's the spirit. Yes, where's the spirit? Should do the awful one or something less awful? I'm looking at this one, I have no clue how to do it. Let's do this. We have, yeah, 26 minutes, we're good. R equals sine squared theta over 2 for theta in between 0 and pi. Have fun.
The beauty of solving the mathematics was always on his calculator.
No cheating. Yeah, talk to a paper sitting next to you if you're stuck. Make sure you are having some kind of progress on this. And also, did I mention you might need trig for Calc 2 or Calc 3? Yeah. Oh, this is easy. Too easy. 3 steps. Yeah, it looked messy, but yeah. I started panicking, but it's fine. drop the mic? All right. That enough? So R prime is 2 sine theta over 2 cosine theta over 2 times 1/2 because of the chain rule. Usually that's where mistakes are. Calc 1. And then Calc 3 after that goes easy. So length would be integral 0 to pi square root function squared, which means sine to the 4th theta over 2 plus sine squared theta over 2 cosine squared theta over 2 d theta. Factor out sine squared, which jumps in front of the root. So you have sine theta over 2. And under the square root, you are left with sine squared theta over 2 plus cosine squared theta over 2, which is 1. I know, all those face palms. So all I need to integrate is sine of theta over 2, which is 2 cosine theta, negative. Theta over 2. Then the answer is 0? No, minus pi. The answer is 2. The answer is 2. So I will plug negative 2 cosine of pi over 2. Minus and minus gives me plus 2 cosine of 0. So this first one goes to 0. And the second one, wait, this is supposed to be 0, not theta. Second one goes to 1. So the answer is 2. If I had the ta-da button, I would push it. How about another 3 examples? Questions, concerns, anything? All right, let's stop the stream. Bye, stream.